How does new information change our perspective on the world? Conditional probability serves as the mathematical engine for updating our beliefs. While the world itself remains unchanged, our lens for interpreting it evolves. Let's take a look at the basic idea of probability and how known conditions change the probability of an event. Probability measures uncertainty. While traditional probability asks for the general chances, conditional probability poses a more focused question. What are the chances after we learn a new fact? This doesn't change the objects themselves, but rather the reference group we use to analyze them. To understand this, let's establish a baseline. If you have a bag of 12 counters, with 5 blue circles, 3 orange circles, 3 blue squares, and 1 orange square, what is the probability of picking a blue one? Well, it is 8 out of 12. In this case, the entire bag is our reference group. The spotlight effect shrinks our reference group. When we add the condition, given that the selected counter is a square, we no longer consider all 12 items. We focus only on the 4 squares, 3 of which are blue. Our new probability is 3 out of 4. This is the language of probability. We write it as P of A given B, where B is the spotlight that narrows our focus to a smaller group, and A is the target we are counting within that spotlight. The math perfectly matches the spotlight. The numerator counts the outcomes that satisfy both conditions, represented by the overlap in a Venn diagram, while the denominator counts every outcome within the new reference group. Consider a school club data set with 30 students. If we know a student plays a sport, we ignore the rest of the school. The condition limits us to the 18 athletes, of which 8 are musicians. Our probability is 8 out of 18. Avoid the direction trap. PAB is not the same as PBA. While the 8 students overlap in both scenarios, the denominators, or our reference groups, are completely different. Always check which group you are measuring against. Sequential actions also change the denominator. If you draw a green sock from a drawer and don't replace it, your starting point for the next draw changes. The condition physically alters the probability of future events. This brings us to Bayesian inference. Let's consider a fruit situation. Box 1 contains 4 apples and 1 pear. Box 2 contains 1 apple and 4 pears. A box is chosen at random. Then, a fruit is drawn and is found to be an apple. Which box is more likely to have been chosen? Because the 2 boxes are equally likely to be chosen, each starts with a 50% chance. Box 1 contains 4 apples and 1 pear, while box 2 contains 1 apple and 4 pears. An apple is therefore 4 times as likely to come from box 1 as from box 2. After seeing an apple, the probability that it came from box 1 becomes 80%, while the probability that it came from box 2 is 20%. The apple provides strong evidence in favor of box 1. We can create a tree diagram to analyze the problem. The probability tree shows every possible path from choosing a box to selecting a fruit. After an apple is observed, the 2 apple paths are compared, showing that the apple is 4 times more likely to have come from box 1 than from box 2. Bayesian inference provides a disciplined way to update probabilities. We start with a prior belief, factor in the likelihood of the new evidence, and reach a posterior probability, an updated view of reality. Natural frequencies make conditional probability easier to see. Suppose we have records from 100 similar mornings, and 32 of them began with cloudy skies. Once we observe clouds, we set aside all the non-cloudy mornings and focus only on those 32 cloudy mornings. Of these, 16 were followed by rain later in the day. So the probability of rain given a cloudy morning is 16 out of 32 or 50%. The clouds give us meaningful evidence and cause us to update the chance of rain, but they do not make rain certain. Base rates matter because we must begin with how common the condition is in the whole population. Suppose only a small percentage of students truly need support. Even a fairly accurate screening tool may still flag some students who do not need support. In a large population, those false positives can add up. In our example, 90 of the 180 flagged students truly need support, so a flag corresponds to a 50% probability. With different base rates or a different screening tool, that probability could be higher or lower. A flag is useful evidence, but it is not a final diagnosis. It should lead to closer observation and additional assessment. Bayes' rule is simply a formal way of comparing the specific overlap of events against the new reference group. It mathematically structures the visual process of narrowing your focus when new information arrives. From weather forecasting to training AI, conditional probability allows us to update our worldview rationally. The world never stops providing new information. The question is, how will you update your lens? A useful caveat for viewers is to slow down and work through conditional probability carefully. A video can introduce the ideas, but the language of given that, changing sample spaces and reversed conditions can quickly become confusing. Pause, draw a table, tree diagram, or Venn diagram, and identify exactly which group is being considered. The goal is not merely to follow a formula, but to understand why the denominator changes and how new evidence reshapes the probability.